Hello everybody, it's time for our last video about spectroscopy, and I've saved some of the best stuff for last. The level of detail of this video is going to be higher than I expect you to remember for class. This is all the sort of nitty-gritties, and we want to take a look at a spectral line itself and look at the details of the shape of a single spectral line to determine a whole myriad of amazing things about a thin gas in outer space. So that would be anything that has an absorption spectrum or an emission spectrum. So let's jump into our spectral line analysis and see what else spectroscopy can teach us about the universe. All right, so just to go ahead and start this, if we were going to look at a spectral line, and here we'll take an emission line of sodium. So right here you can see it has sodium, an emission spectrum, has two emission lines near about 500, let's see here, 1, 2, 3, 4, 5. So 590-ish nanometers or so. So if we were to take one of these emission lines and zoom in on it and look at it in detail, would notice that it's not infinitely thin. It doesn't appear at exactly a single wavelength of, say, 590.0 nanometers. If we look at the line in detail, it has the brightest part exactly where we would expect things. So if we're talking, say, about the hydrogen alpha line, it would have a wavelength of 656.3 nanometers. But then we'd see that the line isn't infinitely thin. It fades out, it gets dimmer as you move away from this central brightest point. The central brightest point is the wavelength that we expect, but the line itself has a little bit of width. So that means that it's giving off light of slightly different wavelengths, not the exact wavelength that we talked about the electron transitioning from one energy level to another. How can that happen? There must be something else going on here, some other exchange of energy that's happening that allows the line to broaden out. And if we can understand what causes a line to be broader or to look different, then by examining a single spectral line and looking at it in detail, then we can start determining all sorts of really cool things about objects in outer space. And what can actually make a line broader? Well, there's a whole bunch of different things. One of them is the thermal motion of particles, something to do with temperature, which means that we should be able to use the widths of these spectral lines as a temperature indicator. We have a temperature indicator for black bodies. Now we're going to have a temperature indicator for things that have emission and absorption spectra. Another thing that can make these lines broaden out is the particles running into one another, exchanging some energy, having collisions. So we can get a measurement of the collisions that are going on, which is controlled by the pressure and density of the gas. So we're going to get a pressure and density indicator. We're going to talk about this strange effect where a magnetic field can split an energy level of an electron. So we'll have an indicator of the magnetic field strength of an object. And then maybe the easiest to understand will be if we're looking at an object that's rotating, we're looking at it in whole, some of it will be rotating away, some of it will be rotating towards us. And that means that a little bit's gonna be red shifted, a little bit's gonna be blue shifted. That's gonna broaden the line so we can tell the rotation of a macroscopic object, something like the sun and how fast it's rotating, or a star. Okay, so let's jump into all of these one by one. I don't expect you to remember the details. I expect you to remember the takeaways that we can determine some property of whatever it is that we're looking at. Say, the temperature of a gas. And we can determine the temperature of a gas by looking at the individual spectral line due to what we call thermal broadening. So here we have an observer, and looking at a bunch of the particles that are in this little chamber right here. The gas in there has a certain temperature, which means that those particles are moving around, and the average motion of all of those microscopic particles would determine the temperature of the gas, right? That's something that we had discussed. That's what we mean whenever we say temperature. But not all the particles are moving at the same speed, and they're all not moving in the same direction. Some of them are moving away from him very quickly. Some are moving away and a little bit up. Some are moving away and a little bit down. Some are moving toward toward and down. Some are moving toward pretty fast. Some are moving toward pretty fast. Some are moving away pretty slow. So we have a balance of each individual particle is going to have some amount of motion towards or away from our observer. And what did we talk about with the Doppler effect? If we have motion towards, then all of those photons are going to be blue shifted. If we're going to have motion away, they're going to be red shifted. Their wavelengths will change a little bit. So we can look and see that, okay, some of them are moving towards them really, really fast. Those wavelengths are going to be blue shifted by a good bit. We're going to get a large blue shift. Some of them are moving towards pretty slowly, so they'll have a tiny blue shift. Some of them are moving pretty fast, but only most of the motion is transverse, only a little bit is towards it. And you start thinking about this, how this distribution would be. By no means something that we're going to have to go over in this class, but most of them are on average not really moving towards nor away, and then you have some that are moving a little bit towards, the motions a little bit towards, and very few that are super high speed where you'd have a very big blue shift. So you end up having this nice little profile of brightest in the center, and then you'd have this tail of blue shifting. And play the same game for the ones that are moving away. Some are moving away really slowly, some are moving away pretty quickly. Some of them have mostly transverse motion, but some of the motion is away. And on average, you'd have a little bit of motion away. And then as you go and talk about larger motion away, that would be fewer and smaller and smaller and smaller. Excuse me. So you end up with this tail of redshift as well. What is controlling the motion of the particles? The temperature of the gas. So whenever you were to look at, say, a line like this in an emission spectrum, you would have a, say, blue shifted tail and a red shifted tail, and they'd be pretty symmetric. So you can measure how broad that line is, and if you have a higher temperature, the motion of the particles is greater, it would get broader, and if you have a lower temperature, the motion of the particles is not as spread out, so you'd have a narrower line. So the width of the line itself can be used as a thermometer. Told you the details of this are pretty complicated, but this is mostly just a combination of what we know of what temperature means with the concept of Doppler shifting. This one's a little bit more nuanced, but maybe a little bit easier to understand, and hopefully this image will help. We have collisional broadening, a change in the wavelengths that the electron will accept to make a transition due to two objects running into one another. So here I have, here I have one object, here I have another object. And in this room, the air particles are all moving around. They're going to be bumping into one another, colliding with one another. And when they do that, they're going to exchange energy. So let's play that again. This one is going to lose energy. This one's going to gain energy in the collision. So one more time. Loses energy, gains energy. And now let's see what that would really mean. This atom lost energy in the collision. So let's imagine a photon comes along right at the same time. And yes, we're talking about lots and lots and lots of photons in a room and lots and lots and lots of collisions because there's lots and lots and lots of particles. So let's imagine a photon interacts with these atoms just as they collide. This one lost some energy. So if that electron is going to make a transition, say jump from the ground state up to the first excited state, and it already lost some energy, it would need a photon with more energy to make up for the loss in the collision. More energy means that it would accept a shorter wavelength. The electron could accept a slightly shorter wavelength to make that transition, a higher energy photon. And vice versa for the other one. This one gained energy in the collision. Oops, can't get my button straight today. This one gained energy in the collision. So the collision itself gave the electron a little bit of energy, and here comes a photon, and it can have slightly less energy because the electron already gained some energy from the collision. So it can accept a photon with a little less energy to make that transition from, say, the ground state to the first excited state. And if it is a photon of lower energy, that means it'll be a photon of longer wavelength, slightly redder. In this case, we'd have slightly bluer, slightly redder, and some collisions are you have a lot of energy exchanged. Some you have a little bit of energy exchanged. So you'll sometimes have a lot of blue shift and a lot of red shift. Sometimes you'll have a little bit of blue shift and a little bit of red shift. But on the whole, you're going to be seeing all of this whenever you're making an observation, which means that you'll see the line, whatever line you're looking at, say hydrogen alpha, 656.3 nanometers, is going to have some width due to collisions. And the shape that the collisions will make, how it broadens the line, looks different than how temperature broadens the line. And yes, it's difficult to tease out, but guess what? We're pretty clever as humans, and we've come up with ways to tease out the temperature broadening from the collisional broadening. And what does this actually do for us? Well, what controls how often things collide and how energetic the collisions are? The pressure of the gas and the density of the gas. Both of those will affect the collisions. These atoms running into one another, exchanging energies. So by carefully looking at the width of the line and doing some really, really careful analysis, we can back out the pressure and the density of the gas as well. So now we have a temperature indicator and a pressure and a density indicator. Let's go ahead and do the softball one before I go into the weird one. And we can use the width of a line to determine how an object is rotating in space. So let's take a star as an example, and I'll have it rotating clockwise here. Here's our observer with some nice 1980s hair. So as the star is rotating, this part right here is rotating directly towards, 100% radially towards. And then here it's split between towards and up and down. Here it's all transverse. Here it's split between away and transverse. And here it's 100% radially away. So you see a lot of blue shift because that's moving towards you, and that's what the Doppler effect does. Things that are moving towards you, this side of the star, have their wavelengths blue shifted. So all of those spectral lines will be blue shifted. Right here, yes, they're blue shifted, but not as much. There's no blue shifting or red shifting because all the motion is transverse for this part of the rotation. Then a little bit red shifted, then a lot red shifted. Put that all together because you're just observing the star. And instead of having this nice narrow line at say 656.3 nanometers, it's spread out. And how that is spread out is due to how this rotates. Again, we can tease that out from the other effects. And it gives us a way by how broad it is. If it's spinning faster, more blue shift, more red shift, you'd have a broader line. If it's rotating slower, a narrower line. So you can tease out, and remember with the Doppler effect, not only can we detect the direction of motion towards or away, but also back out the speed. So we can figure out the rotation period of this star. We can figure out how the star is rotating. So rotational broadening. So we can determine the rotational state of not only stars, but of things like galaxies as well. This is what Vera Rubin used to determine and give us an indicator of dark matter. And now the weird one. And let's just go ahead and there's a quantum mechanical effect, and we know quantum mechanics is strange. So I'm going to ask you to just trust me on a lot of this instead of going into like the details of talking about quantum numbers and magnetic moments and how exposure to a magnetic field can cause a electron energy level to split. In this case, it's splitting the 2p electron orbital is splitting into 3 different energy levels. So what was 1 energy level is now 3 energy levels. And what is causing it to split? This will happen. Some energy levels will split into multiple energy levels in the presence of a magnetic field. And how widely they split, so how much space there is between these, is determined by the strength of the magnetic field. They'll split wider with a stronger magnetic field. So this is called the Zeeman effect. I know it looks like Z-man, but it's pronounced Zeeman. And really what this is telling us is we are going to have a way to determine the magnetic field strength of objects if we observe this line splitting effect. So we have this one spectral line that's one electron energy level split into three separate ones. So we could have this transition, this transition, this transition. And the electron will make over all the atoms that are there, the electron will be making all of those transitions. So what appeared as a single emission line will now appear as three clustered emission lines. And how much space in wavelength there is between them gives us an indicator, a way of backing out the magnetic field strength. This is how we determine the magnetic field strength of the sun. This is how we know that sunspots, so we're zoomed in on the surface of the sun and here is a sunspot. This is how we know that sunspots are associated with the magnetic field of the sun. So you can see this vertical line going through here, and we're going to take a spectrum along this vertical line. So you can see where it's not in the sunspot, you just have a regular spectral line. And then as you go over the sunspot, you see this spectral line split into three separate spectral lines. Why? Because there's an intense magnetic field right there that splits these lines. And by how much it splits, we can determine the magnetic field strength associated with that sunspot and start mapping out the magnetic field of the sun and the magnetic activity of the sun, and many other things as well. So, all sorts of really cool things, but I want us to step back because this is the last I'm going to talk about spectroscopy for now. I mean, it comes up all the time in astronomy because it's incredibly useful. But this was a pretty intense part of the class, spectroscopy. New ideas, all sorts of little tiny nuances running around. Quantum mechanics is all of a sudden important. It deals with some pretty heady ideas. So it's really important for us to step back for a moment and realize just how much we have accomplished. So remember, we are just getting light from celestial objects. And now we can break that light up by its wavelengths, its spectrum, and by analyzing its spectrum, that light is giving us an incredible wealth of information, making spectroscopy one of the most powerful tools in the astronomer's tool belt. The advent of spectroscopy revolutionized our knowledge of the universe. So let's see and be proud of what we've accomplished so far. We can go ahead and look for where the spectral lines are, where their wavelengths are. We see 656.3 nanometers, 486.1 nanometers, and the other hydrogen bomber lines, we know that that gas is made out of, or that object is made out of hydrogen. We see lines associated with helium, we know it's made out of hydrogen and helium. We see it also has lines of carbon, hydrogen, helium, and carbon. So just by where the presence of emission and absorption lines, associating those to the wavelengths of the emission and absorption spectra of the elements, gives us the chemical composition. So we have a chemical composition indicator. We can determine what stuff is made out of and the relative abundances if we're careful. We have a temperature indicator, and we have two ways of determining temperature. We can use Wien's law for things that are acting like black bodies, or we can use this thermal broadening of an absorption or emission line. So that boils down to, it doesn't matter what object you're talking about in the universe, we can determine its temperature. All we have to do is measure its spectrum, and we have ways of determining its temperature. We can determine how things are rotating, whether that's stars, planets, or galaxies. We can determine how things are moving using the Doppler effect. Well, unfortunately, we can only tell the motion towards us or away from us. But that's a critical thing to be able to tell. It allows us to map out how the stars are moving locally. It allows us to map out how the stars are moving in the Milky Way galaxy. It allows us to look at the Andromeda galaxy, our nearest neighboring galaxy, and determine that in a couple billion years, the Andromeda galaxy and the Milky Way galaxy are going to collide. We can look and see that all the spectral lines of the Andromeda galaxy are blue shifted, which means that it's coming towards us. So we can use the Doppler effect to determine radial motion. We can look at this collisional broadening, the width of an individual line, to determine the density and pressure of a gas. And we can use this strange Zeeman effect to determine the magnetic field strength. And this is just a short list of sort of the bigger ones. But look at all those properties of a celestial object we can gain just from the light and using spectroscopy: chemical composition, temperature, rotational state, its motion, its radial velocity, the density, the pressure, and the magnetic field strength. That is a plethora of knowledge about the celestial objects. And we're all on the same page now. We've all just went through spectroscopy. This is really like pulling back the veil on the universe and being able to see some of the deepest mysteries shed with light shed on them. Pun slightly intended. I hope you enjoyed this unit on spectroscopy. I know it was difficult in concepts, but oh, what we've gained from it. It is just incredible. And I say this knowing that I'm a spectroscopist, so I'm a little bit biased here, but it is really, really cool. And I hope you gain an appreciation of that.